But you know, it's a lot of fiddling around, and sometimes it's difficult because it seems like it's tough because you have all these extra things, but you know, you don't really pay attention to the extra stuff because they cancel out at the end. Things like, you know, there's no water in here, but we never really worry too much about water. We just worry about the main substances that we did. All right, are there any questions before we get started? What I'm going to do is I'm going to give you, well actually, maybe I can give you a brief overview of what we did in Chapter 7. In Chapter 7 we talked about heat, right? And there are two different kinds of heat. There's heat that's related to a object, and there's heat that's related to a process or reaction. And you got to keep those. And so the heat related to the object is the mc delta T, or the amount times C times delta T. The heat related to an object is?
Calorimetry?
Yeah, it's calorimetry. There's two types. There's coffee cup and bomb. Yeah. Coffee cup, the heat would be equal to amount times delta H. You know, for bomb, the heat would be equal to the amount times delta U. And so these things you kind of drill just over and over in your head until you get it. And then there's work, right? And then state functions. There's only one type of work that you need to be able to calculate right now, and that is the P delta B work, which is a pretty simple calculation. And so then we talked about total energy, or the internal energy, which is related to the, actually the total energy is equal to the, what? Potential energy and the kinetic energy. Then,
The total energy is same as the internal energy?
Yes. Total energy and the internal energy are the same.
That's delta U, right?
Delta U, right.
But that's delta, but can you calculate internal energy? Not the delta U.
Can you calculate, I'm sorry, each energy?
Can you calculate internal energy total?
Internal energy
Not the
total.
delta U.
Yeah, you mean U. We call that absolute internal energy. That's a good question. Can you calculate the absolute internal energy? Yeah, you could calculate it. You have to figure out the potential energy and the kinetic energy. Kinetic energy is easy because that's the temperature. Potential energy, people work at calculating this, but the calculations are pretty inaccurate. The reason the calculations aren't so accurate is because
You have to look at
they don't know the total energy stored. You know, an atom, how much energy is stored in an atom? And so you think about the atomic bomb or something like that, and there's a lot of energy stored in the atom, because if you break apart the atoms or even fuse them together, there's a tremendous amount. But is that all the energy? If you were to take an atom and then extract all the energy by breaking it apart completely, how much total energy would you get? That would be the potential energy, right? And so when they break apart, you know, it could either cost energy or release energy depending on how it is, but, you know, where does it stop? That's the problem. And so the problem is this potential energy cannot be calculated accurately. It's estimated, but it's pretty useless. Cannot be calculated accurately. It's pretty useless for calculations because the error, you know, the error associated, if you look at the error bars, you know, the plus or minus, you know, whatever the error is that we think about this, the error bars are typically much bigger than the delta U's we're interested in. And so the delta U's are small compared to the errors. And therefore, this is not really done. This goes for the same. This is the absolute internal energy. It's the same for the absolute enthalpy. You don't calculate those because the absolute enthalpy depends on the absolute internal energy. So both of those are not determined. I mean, you could factor out certain things. Like, for example, in chemistry, the nuclei don't really change. So you don't worry about the energy contained in the nucleus. And then you can look at, but that's not really the absolute energy, because if you ignore the nucleus, right? There's a lot of energy stored into the nucleus, because how much energy is required to hold a whole bunch of protons in a very tiny space? Huge amount of energy is required to hold that together. And so if you break it apart, what happens to all that energy? All that energy is
was released. Well, how much energy is that total? And so we have the nuclear binding energy per nucleon, so we could calculate that. But then there's a problem, you know. If you break apart the proton, can protons break into smaller pieces? And how much binding energy is holding those smaller pieces together? And so, yes, the proton can actually break. People are looking for proton decay, you know, the decomposition of protons, right? Well, anyway, so does that answer your question? The absolute energy. For example, in physics, you know, you simplify things, because in physics, let's say we just look at the gravitational potential energy, and that's it, right? And so, like the mountain climber, that's all we're looking at. This is higher gravitational potential energy, lower gravitational. In chemistry, we should also look at the gravitational, you know, as part of this as well. Do we? We should, yeah, it should be factored in, too. Gravitational. But it's so small, you know. Or is it? I don't know. In changes, you know, changes would be small. But so don't calculate absolute. These are not determined. Therefore, whenever you do delta U, you don't get U final minus U initial. You get Q plus W. And so this we don't do, but this we do. Delta U's are accurate. You know, these can be accurately determined. Delta U can be accurately determined. However, U's cannot. And so the changes are easy to pinpoint. There's the cows. All right, so we talked about internal energy. We talked about enthalpy. You know, for us, what's more? Delta H is more useful. And so then we think about the ways of getting delta H. You know, the ways of getting delta H is calorimetry. Yeah, you do bomb, you get delta U, you convert that into a delta H. Or you do coffee cup, you go straight to a delta H. But there are alternative ways of getting delta H. We don't always have to do calorimetry. We could also do Hess's law. Hess's law like this, or there's a much easier variation where you don't have to write out all the equations. The reason you don't have to write out all the equations is because they're all formation reactions. So the extra bits are all elements in their standard state, so they automatically cancel. The extra bits here aren't all elements in their standard state. Here, for example, water. You know, that's an extra thing. We don't want that down here. And so for Hess's law proper, we have to write out the equations and make sure everything cancels. For the formation version of Hess's law, we don't have to write out all the equations. We just do the sum of the delta H's of the formation of the products minus the sum of the delta H's of the formation of the reactants. And everything else cancels, so we don't worry about all this work. This is a lot of work here to do this. And so by far the easiest way to determine delta H of reaction is not calorimetry. It's not this version of Hess's law. It's by using Appendix D. Yeah, the table. The only problem with using Appendix D is it's restricted to what? 1 bar and 298 Kelvin. So if you're not at 298 Kelvin and you're not at 1 bar, these values are not accurate. And so that's the only problem. But fortunately, 1 bar and 298 Kelvin is the most common conditions that we use. In fact, what is more common, 298 Kelvin or 1 bar? 1 bar. There's more disagreement because there are people who work at alternate, you know, different temperatures. Like, for example, the biologists will say, no, 298 Kelvin is not useful for us. What is useful for biologists? 298 Kelvin is not very useful for biologists. Everything in biology, all the thermodynamic tables aren't to 290 Kelvin. All the thermodynamic tables are to, you know, like body temperature, yeah, for biochem. Yeah. And so you see a lot of body temperature data rather than 298. And so that means since people want their own temperature because not everybody's the same, then because a heater is easy to have, a heater, you just heat it up. There's no standard temperature. You can't get agreement. But there is standard pressure because nobody wants to pressurize a room, right? Or vacuum their room. That's too much hassle. And so standard pressure, no problem, but standard temperature, you're going to get arguments about that because some people want this temperature, body temperature, other people want room temperature. And so this is why, it seems obvious, come up with a standard temperature, but they didn't, because people want to use different temperatures. But pressure's more difficult to change. And so once we have a delta H, then we can apply it to a stoichiometry problem. It's a conversion factor, and that's the last thing we did. How many moles of glucose were required. And so ultimately we want to be able to do energy calculations for chemical reactions, and we want to get an accurate number. We want to get a number like if you burn a mole of glucose and you get this much energy, everybody should get the same, right, amount of energy. That's delta H. That's called the state function. Although, the 70% efficiency could change. The efficiency of converting that energy to work depends on the path. And so that isn't the state function, efficiency. All right, that's chapter 7, pretty much, in a nutshell. Let's do, what I'm going to do for chapter 8? I'm just going to summarize the whole chapter because we're kind of behind. I'm kind of behind schedule. So I want to summarize the whole chapter, and then we're going to look at bits and pieces of that chapter to understand certain concepts better. Okay, what does chapter 8 deal with?
Electrons, like electron shells and
that kind of stuff. Chapter 8 is basically is quantum mechanics. That's what the physicists call it, quantum mechanics. And you know what the chemistry calls it? The chemists call it sometimes. Instead of quantum mechanics, they call it quantum chemistry. So what's the difference between quantum mechanics and quantum chemistry? Nothing. They're the same thing, right?
you just personalize it.
Maybe it's a little bit different. Maybe not.
Maybe emphases, they emphasize something else.
Yeah, maybe quantum chem emphasizes more molecules, but it isn't like that really when you look at it as a whole. And so chapter 8 we'll call quantum mechanics. And so let me tell you, what is quantum mechanics? Quantum mechanics is mechanics. This is also called quantum chemistry or quantum theory. And so what quantum is it's a theory, quantum theory. And so what again is a theory?
It's an explanation.
Yeah, it's a very detailed description of nature,
Natural law.
yeah, just how nature operates. This is what, ultimately, what scientists do? What scientists are very good at? Scientists are very good at observing nature. They just watch, and eventually, they get some patterns, right? But I was listening to this other TED Talk just the other day, and it was a sociologist, and the sociologist was looking at something about human behavior, and when I was listening to that, she said, okay, she went into a research mode. When she went into research mode, she just looked at the data, and she said, eventually, by looking at the data so many times, she came up with some patterns of human behavior. And then some kind of hypothesis, and then some type of theory as far as, people behave this way because of this. And then I thought, wow, that's the scientific method. And so, even in the social sciences, they follow the same kind of thing. And what is the same kind of thing? The theory is ultimately what we want, because the theory is the fundamental, the detailed description. It's like watching atoms, and then, you see some type of behavior, and then you try to figure out why, some kind of connection between that behavior and whatever. And so this is it. We look at this, quantum theory, quantum mechanics, quantum chemistry is basically a theory, and a theory is ultimately this is our goal, right? Our goal is a theory, because a theoretical understanding of everything means you can predict anything, right? If you understand the theory of everything, you can predict anything. Although you'll find out that the quantum theory tells you can't predict everything, because it's just a fundamental part of nature, is you can't predict everything. But anyway, going back to this, up to when it gets very small, we'll talk about it. But is there something at a higher level understanding than a theory? Some people say, I always hear hypothesis. A hypothesis is a higher level of understanding than a theory. Is that true? No. Hypothesis is your initial tentative guess, right? Is an experiment? Well, the experimentalists will always say experiment trumps theory. You see a lot of theories thrown into the waste bin here, the garbage can, because it conflicts with experimental fact. So if your theory conflicts with experimental fact, then it's not good, right? Some people are worried. I was listening to some physicists talk, and some people are worried. They're worried that, yes, their theory seems to fit all the data, but they're always worried that, maybe it's just by chance. Maybe one day somebody's going to observe something that conflicts with all their theory, and they have to throw it in the waste bin. And so what are the odds of that? So far it's good, so far so good, but in the back of their mind they're thinking, because it's happened, it's happened many times where the theories have gone by the wayside, as we'll see here. Well, anyway, so the social scientists, when she was talking about coming up with this theory of human behavior, then I thought, wow, this is exactly what I did, and exactly what I'm telling you is exactly what I did, and exactly what everybody in my research group did, exactly what everybody on my floor did, exactly what everybody in the whole building did. And what was that? Observation. And so scientists are very good at observation. Most of the people I ask, what do you do? Observe nature. That's it. And then what?
Look for patterns.
Look for patterns or trends, and then what?
You make a hypothesis of what might be.
Yeah, you make these patterns and trends have to be consistent.
With a law.
And so you could have a law. Is this law based on theory? Are laws generally aren't based on theory. Laws are just based on patterns. You see a pattern, you fit it with a mathematical equation, that becomes the law. For example, the ideal gas law. How was the ideal gas law derived? The ideal gas law was observation of gases, patterns, and then they came up with a mathematical equation that describes the pattern, PV equals nRT, and that's it. That's where we stopped here, right? But what is the fundamental description of the ideal gas law? Could you derive it from what they call first principles physics for me? Derive the ideal gas law? No, because the ideal gas law, you could, if you actually you can. After this is a basic, this is what we call an empirical law. Have you heard of an empirical law?
Yeah.
Or empirical formula?
Based on data.
It's based on observation. It's a law that just fits your observation. Newton's equations. If you think about Newton's equations, very famous equations in physics, where did those equations come from? Are those from observation, empirical, or are those from the theory of the universe? So those are just strictly mathematical equations that fit this, how fast, time. it's very simple. Anybody could do it, right? If you just observe it, you try to fit that mathematically, you know? That's it. Not everybody can do it, because Newton would say, you know, calculus and all that other stuff, it's not so easy to do. But anyway, here, this law, you know, even you could have done this. You could have come up with a graph that described the gas behavior, and then you could have come up with ideal gas law. Maybe name it after yourselves. Well, anyway, that's a law, but people are thinking, now, why is it PV equals nRT? You know, what is the underlying fundamental description of what's happening there? And so in chapter 6, then after the law, we started talking about kinetic molecular theory. And so kinetic molecular theory is the theory underlying this ideal gas law. You know. And so, but before the theory came, you know, not everybody's going to accept it. We have a hypothesis, and then the hypothesis leads to a theory. So anyway, this is the development of quantum mechanics in a nutshell. And so quantum theory, right here, was derived from observation. And so what were the observations? The observations were this: unusual light patterns. You might not think they're unusual, but you know these lamps here? Oops, I didn't know the lamps were set up today. I should have told her. Somebody had just asked me about this. Sorry. She left. I think somebody was going to try to make it out. But anyway, we have the unusual light patterns, and I'll talk about why they're unusual light patterns. These patterns, at least the hydrogen one, the hydrogen atom fits a mathematical equation. And so for the hydrogen pattern, they saw, you know, the pattern in the wavelengths fit a mathematical equation so that, you know, they could make predictions about what other wavelengths should be observed based on the pattern. This pattern, you could call it a law or an equation, but this led to the Rydberg equation or law. The Rydberg law is just, you know, just like PV equals nRT. You know the pattern, you can kind of predict how the pattern continues. And so we have the Rydberg. And the hypothesis that came up from this is that electron energies in atoms are quantized, not continuous.
What do you mean by quantized?
What's quantized?
Quantized means that,
You can count it?
no, all quantized means is that there are forbidden energies and allowed energies, whereas continuous means all energies are allowed. And so quantized just means there are forbidden and allowed energies.
What does that mean?
Okay, let me say, you're driving your car along, and if the speed of your car is quantized, that means that you can drive, let's say, 5 miles an hour, 10 miles an hour, 15 miles an hour, but you couldn't drive 6, 7.5, 1.3. You couldn't drive those. It has to be 5, 10, 15. This is like there's a button on your stove, or something. You have three power settings, low, medium, and a high, but nothing between. And so you can either set it and it just clicks. Low, click, medium, click, high. Continuous means you have a continuously adjustable knob So you can adjust it, the flame, anywhere from low to high. Okay. That's what it means.
And so continuous just means all energies are allowed. All are allowed.
Quantized means not continuous distance.
Quantized means not continuous. It jumps. The thing is, it's like the floors of a building.
The floors of a building are quantized. Let's say you want to go, you go to a big building, tall building, and you want to go to the 1.4 floor. Are you going to find the 1.4th floor? Is there a little knob you can adjust so the elevator stops at the 1.4? Or let's say 1.41, 1.42, 1.4235 floor? No, it doesn't work that way. The elevator's quantized. It's going to stop at the first, second, third floor. That's quantized, you know. Or the steps of a building. In Chem 4, they show this. The analogy here is steps. If you walk up the steps are quantized, whereas a ramp is continuous in terms of gravitational potential energy. In terms of gravitational potential energy, you could be here, here, or here, but you can't be between. I mean, let's say I want to stop a half a step up. There's nothing to step on, right? So you can't stop there. And so steps are quantized, ramps are continuous. You know quantized and continuous, actually. Let's say you're adding a sugar cube, plop, and you just want it, your coffee's just not quite sweet enough, you know? Not quite sweet enough. I want a half a molecule of sugar extra, you know, and then it'll be perfect. Can you get a half a molecule of sugar in there? No, you're stuck. You're going to have to add a full molecule. And then you got a full molecule, maybe it's too sweet, but you're out of luck, right? But we don't notice sugar. Do you ever think about sugar being quantized? You know, I want my coffee has to jump up to the next level of sweetness. Do we ever notice that? We never notice that because can you taste the difference between 99 versus 100 sugar molecule? You can't, right? You can't. And so in normal everyday life, do we notice things being quantized? No. I mean, even like gasoline. You think gasoline, when you're filling up your tank, is actually continuous. You can get any number of gallons you want, right? In the macroscopic world, it is continuous. 1.1 gallons, no problem. But, you know, when you get to the molecular level, can you get any amount of gasoline you want? No. It's going to be quantized in terms of molecules. We just don't notice it because we
Experience the world.
we deal with the macroscopic world. And so this whole thing is, you know, I talked about Newton's law. Newton's law is what we call classical physics. And classical physics turned out to be not complete. Classical physics wasn't a full description of nature. It turns out that classical physics should be replaced by quantum physics. But, you know, classical physics was good enough to get people to the moon and back, and it still is. You know, but anyway, it's because you just don't notice those small steps. The steps are so small that it appears to be continuous. When you get to things where, you know, the quantum behavior, and why we're talking about this is when we're dealing with single atoms, you know, single atoms, things are going to be quantized in terms of amount of matter, but they're also going to be quantized in terms of energy, which is unusual because you wouldn't think energy would be quantized. But anyway, let me continue on with our quick summary here. This led to the Bohr theory.
theory won. The Bohr theory. But, Bohr theory is one of those things where they realize that, hey, the Bohr theory doesn't work for everything. You can't make predictions. And so the Bohr theory was good at describing hydrogen, but that was it. Anything more actually hydrogen and some other unusual species. So the Bohr theory was dropped. Not everything in the Bohr theory was dropped, but parts of it were dropped. Bohr theory, the basic description of Bohr theory is that we have orbits. And so this would be like a satellite orbit, so electrons orbit around the nucleus. Orbits. But orbits turns out to be wrong.
Orbital.
Yeah, right. And this led to what we have now. This is our modern day theory, which is quantum theory. Quantum theory doesn't talk about orbits, it talks about orbitals, which are totally different than orbits. And so this is chapter 8, pretty much. We should spend most of our time talking about orbitals and quantum theory, but we need to talk a little bit about the development of quantum mechanics here. And we should spend some time talking about light, because this is what started all of this. There's unusual light patterns that had to be figured out. So, let's go on here. Let's talk about light first. What is light? And so just some basic background review about light. Light is, photons, or light is electro for electric fields, which we'll talk about oscillating magnetic for magnetic fields, electromagnetic radiation. That's what light is, right? Electromagnetic radiation.
Yes, definition.
Yeah. So when we think about light, electric, what is the electric part of this? The electric part is we have what we call an oscillating electric field. The oscillating electric field we can show via waves. And so here we go positive, here positive, negative, positive, negative. And then when we generate electric fields, it turns out we also generate magnetic field. And so there's going to be a magnetic field which is perpendicular to this. But it'd be oscillating, and you got to correct me if I'm wrong. I'll just write it: North Pole, South Pole, North Pole, South Pole, like this. I might have, I got to think about the right hand rule for this. I might have it backwards. But anyway, we got this oscillating electric. Now, oscillating electric fields, it's like this. We know, actually, we're going to ignore the magnetic field, and we're just going to focus on the electric field. We know that plus and minus are attracted, but plus and plus are repelled, and minus are repelled. And so think about this. What do electric fields interact with in matter? Electric fields interact with charged particles in matter. So what are the charged particles in matter? So for example, if you're a neutron, are you going to be influenced by the plus and the minus oscillations like this? No. What do you think would be influenced by the plus and minus oscillations like this? Protons. If you're a proton, how would you be?
You will be going.
Yeah, you'd be attracted, negative, this should be positive here. Protons are going to be repelled, so, they're going to be down, right? Basically, if you're a proton
and you're exposed to this field that's oscillating back and forth like this, you're going to start oscillating
With the negative.
back and forth like this, right? The protons are pretty massive. What do you think would be, there's some inertia there. It's kind of massive, steady. What do you think is very light and easy to push around? Electrons. And so electromagnetic radiation interacts primarily with electrons in matter, because electrons are charged particles, right? There's nothing anchoring them in space. Are they fixed in space? No, they're free in space. So along comes this electric field that's going up and down like this. The electron's going to start going up and down like this. And so the electrons are going to couple with the oscillating electric field. Okay. Now, light, do you know how fast light moves? Yeah, these waves move at a velocity, I'll call it nu, which is equal to the speed of light. Speed of light is incredibly fast, 10 to the 8 meters per second. Everybody knows speed of light's fast because, like, for example, radio waves travel at the speed of light, so you can hear live broadcasts, right? Well, I was listening to another radio program about Mars. If you have waves traveling at the speed of light, to communicate with somebody on Mars, it would take 40 minutes. So they're talking about how would you have a did you hear about that? How would they have a conversation? Because hello, 40 minutes later, hello. Can you imagine that? Yeah. So I get it's incredibly fast, but not that fast. If you lived on Mars, But anyway, it's moving fast. This is like instantaneous. So if somebody shines a light over there, instantaneously you're going to see it because it's moving at 10 to the 8 meters per second. Because it's not going to take very long to reach you. Now, if you're an electron, this field is going to be oscillating fast, right? We call this frequency. And so if you're an electron, it's like this. But it depends on, the wavelength of the light, right? The wavelength is the peak-to-peak distance. The peak-to-peak distance we call what symbol here? Lambda. And so if we have a short wavelength, it's really tight, the waves, then it's going to oscillate very fast, like this. But if the wavelength is very long, then it's going to oscillate a lot slower. And so we call that frequency, this oscillation. In fact, frequency is how many of these peak-to-peak wavelengths pass by. So it's a cycle. This is called one cycle here. And so the frequency, actually I shouldn't use this nu, I should just use c. Speed of light is given by, let me change the symbol, c. Do you know what we use nu for? Nu is for the frequency. And the frequency is going to be in units of cycles per second. A cycle per second is called a hertz. So one cycle per second is a hertz. So, like, if you're listening to FM radio is megahertz. Megahertz is 1,000,000 cycles per second. And so that electron is oscillating at 1,000,000 oscillations per second. That's fast. But there's even faster frequencies than that. And so this is light, the speed of light in a vacuum. It's constant. And so we could do some simple calculations. The speed, lambda, and nu are all related. And so what is the relationship? Well, c is equal to mu times lambda. And so from this we can derive lambda is equal to c divided by nu, or nu is equal to c divided by lambda. Is that right? And so let's check the units here. Because c is going to be in meters per second, nu is going to be in cycles per second. We usually just call it seconds to the -1, because cycles we don't give a unit for. Hertz is also seconds to the -1. Lambda is in meters, so meters per second. That works out using dimensional analysis. And so the faster the frequency, that is, the higher the frequency, the shorter the wavelength, right? And vice versa. The lower the frequency, the longer or the bigger the wavelength. And so what we're going to do is we're going to characterize light. We can either characterize light using frequency or we could characterize light using wavelength. We do both, actually. It depends on which one's more convenient to use. And so, for example, microwaves. Microwaves are usually characterized by short wavelengths, right? Microwaves are actually both. Both frequency and wavelength are common for microwaves. So a lot of people know microwave is like 2.4 gigahertz. Wavelengths are like 8 centimeters, 9 centimeter. 9 centimeter, think about this. If you have like an 8 centimeter wavelength or 10 centimeter wavelength, that's like this, peak to peak distance. But since it's moving at the speed of light, you have 2.4 gigahertz or 2.4 trillion, is that right? Giga. Mega comes after mega. Giga. So mega is a million, giga would be a billion. And so 2.4 billion of these cycles passing by every second, which is fast. Well, anyway, so let's look at the spectrum, the electromagnetic spectrum, EM spectrum. If we look at the EM spectrum, we can look for based on lambda. Let's go increasing lambda. And so we're going to start off at the shortest wavelengths. Do you know what has the shortest wavelengths? Gamma. Gamma rays. Gamma rays are short wavelength light. Short wavelength means high frequency. And so short, lambda, high, mu. And so how short? Like, 10 to the minus what? 10 to the minus 30? Is that right? What is 10 to the minus 30? 10 to the minus 20? Something, incredibly short wavelength. And then from gamma rays, if we go a little longer wavelength, we call them X-rays. And a little longer wavelength we call UV or ultraviolet. And if we keep going longer wavelengths, then we're going to get to... Yeah, but before we get ultraviolet, then we have what's called visible light. Now, visible light is made up of different colors. And so the shortest wavelength of visible light is violet. And then indigo. And then blue. And then green. Yeah. And then yellow, orange, red. Are you guys familiar with this? Roy G. Biv, spelled backwards. Roy G. Biv, why did I spell it backwards? Because we're going from shortest wavelength to longest wavelength. The reason I'm doing shortest wavelength to longest wavelength is because that's what the LabQuest does. Did you know this? It was violet on the left and red on the right. And so that means ultraviolet is past violet, and then to the right of red, we can't see it, it's infrared, IR. And then even longer wavelength than infrared. Infrared is micron wavelengths, and then we go to microwave. It gets to much longer wavelengths, like centimeter. Wavelength of microwaves on the order of centimeters. And then radio and TV. Okay, what wavelength should you know? You should know red. The end of red is what? 760 nanometers. The end of violet is about 390 nanometers. And so we go from about 400 to 800 nanometers across the visible spectrum. The visible spectrum is actually, the only one part of this we can see. The rest is invisible. And the visible spectrum just makes a tiny fraction of the total electromagnetic spectrum here. And so IR, what would you say? What's IR? IR is usually thousands of nanometers. UV is less than, like 100, less than 100, tens to, or ones to hundreds of nanometers. And so, we'll just say less than 390. Then we have different ones. We have something called near, mid, and far, right? Near would be, like 200. It's near violet, right? 100 would be like near. 50 is probably near. As you get smaller, like tens or ones, then it's probably mid, and then further out would be far, UV. And the same thing with IR. We have near IR, like 900 nanometers. Is that near red? Yeah, that's near red, so we call it near IR. And then there's mid IR. Mid IR would be like 3,000, to maybe 10,000. And then far IR would be probably greater than 10,000. Well, 10,000 nanometers is 10 micrometers. And so IR, oftentimes they talk in terms of micrometers, like 1 micrometer, which is 1,000 nanometers, to 2 micrometers, which would be 2,000 nanometers. Does that make sense? And so typically those. And so you should know this because, sometimes we want to know where is that radiation in terms of wavelength. If you're looking at radiation of 1,200 nanometers, then you're thinking 1,200 nanometer radiation is, tell me, without looking in a book, 1,200 nanometer radiation. IR. 250 nanometer radiation. It'd be UV. So this is 400 to 800. So what's halfway between 400 to 800? 600 nanometer radiation. Guess. 600 nanometer radiation. Guess. Color. Probably green. Somewhere around there. Maybe yellow, maybe blue. Somewhere around here, right? But at least you know roughly where it is, right? 600 around green. Does that make sense? And so all of this because you memorize. You have to memorize two. And so memorize these two. All right, the other wavelengths we aren't going to worry about, but the wavelengths range from the smallest, wavelength, way smaller than an atom, these wavelengths, to huge wavelengths. Radio and TV, do you know how long the wavelength is for radio wave? Like a kilometer, some of them. And still, it's like kilohertz, 1,000 of those in a second, 1,000 kilometers in a second. And so, wavelengths range a huge amount, therefore the frequencies are going to range a huge span, many, many orders of magnitude. But am I going to ask you to memorize those? No. Well, when we're talking about low frequency, it's still kilohertz is not that low, is that? Or it doesn't seem all that low. Okay, next, we're going to talk about energy. Gamma rays, is that high energy or low energy? This is high energy. What can gamma rays do to matter?
pierce it.
Well, it doesn't really pierce it.
I feel like it goes through it.
It knocks, well, gamma rays are like this, crazy frequencies, right? You get an electron oscillating like that, what's going to happen? Eventually it's going to get knocked off. And so what do gamma rays do? Gamma rays ionize matter, right? They take the electrons and knock them off. So this is ionized matter. How about X-rays? Can X-rays ionize matter? Yeah, X-rays can ionize matter also. Knock off the electron. And so gamma rays and X-rays are called ionizing radiation because they have enough energy to ionize matter, which is related to the frequency. Right? And so it turns out, I'm going to talk about this, but the energy is proportional to the frequency, and it's inversely proportional to the wavelength. How about UV? Does UV have enough energy to ionize? No. What happens with UV is, let's say you're an electron sitting in matter. You're an electron in a bond, right? And this UV ray comes out, and the electrons in the bond start oscillating, but they don't oscillate enough to knock them off. They oscillate enough to break the bond. And so what UV does is it breaks bonds in matter. And so bond breakage. But not quite enough energy to ionize. And so UV is not really considered ionizing radiation. These are very general because you got to look at, the amount of matter, what type of matter it is. How about visible? Is visible light enough to break bonds, like say your DNA? No. Visible light is just, visible light doesn't break the bonds, it's just going to excite the electrons in matter. So visible light excites electrons, but not excited enough to ionize and not excited enough to break bonds. Just excite the electrons. How about infrared? Infrared, when we talk about visible is enough to excite the electrons to pretty high energies. But infrared, when it interacts with matter, then it's not really, the electrons are kind of tightly held. But you have these molecules, and these molecules are polar. You guys know what a polar molecule is, right? What is a polar molecule? It's charged. One end of the molecule is positive, the other end is negative, like a water molecule. And so IR is really not enough to excite the electrons in the hydrogen-oxygen bonds because the electrons are so tightly held in those bonds. But you got this big molecule. IR is enough to start, actually, I should say more. IR is enough to start the molecule vibrating. And so you got a bond here, and then you're looking at the bond dipoles. And the bond dipoles, you got a positive end and a negative end, and those bond dipoles can start moving based on interacting with the electric field. And so if you have a bond dipole, what will happen is it'll start vibrating with the oscillating electric field. Microwaves, though, microwaves aren't enough to oscillate that bond. The microwaves are only enough to rotate these polar molecules. And so microwaves can rotate molecules. This vibrates bonds. Rotate molecules. Radio and TV, what do those do? Well, we're running out of energy, aren't we? What do radio waves do? Radio waves can this is low energy, right? Radio waves are low energy. And so we got to think, what can radio waves do? Well, let me move this a little bit. Radio waves can excite electrons, but didn't I just say visible does? Radio waves can excite electrons in only a few select substances. What are they? Excite electrons in metals.
Why is that?
Why is that? The reason that is because metals are so loosely held. Radio waves are so weak, right? If you try to make a radio antenna out of a piece of plastic, oh, plastic has electrons in it. I'm going to make a radio antenna out of plastic. Is it going to work? No, because the electrons are so tightly held in the plastic that they aren't going to be excited by radio waves. You need like a piece of metal. You need a piece of metal to have the because in metals, are the electrons really tightly held? No, they're very loosely held. Metals are good reducing agents too because of that. But radio waves come along, they can couple with the electrons here because electrons can easily oscillate, whereas electrons in the pen here aren't going to be easy to oscillate. Does that make sense? And so we can excite electrons in metals, low energy. So that's it. So that brings us to this. It's very easy to excite electrons in metals. And so we can see what happens as we excite electrons in metals. And so let me just show you what happens when we excite electrons in metals. The striker is missing. They clean up the lab, but somebody cleaned up the lab. They ended up moving the striker. I need matches. Does somebody have matches? I'll get some matches. I need to get some matches. Oh yeah, what's another way, radio waves can excite the electrons in a metal, right? But what's another way to excite the electrons in a metal? Heating it up. So I'm going to heat it up and try to excite the electrons in the metal. Let's flip off the light.
What metal is that?
Probably metal.
This is stainless steel here. Some iron. Alright, so I see the flame here. What's the hottest part of the flame?
In the metal?
At the tip of this inner cone here. Oh boy, this has a lot of junk on it. Do you see the yellow color?
Yeah.
It'll burn off. I just hope there's nothing more nasty than that. There's nothing. Alright, and so one way to excite the electrons is like this. I put it in here, I excite the electrons, I remove it, and then I can feel. You know what I feel here?
Heat.
Heat. Heat is infrared radiation. Infrared radiation. Can I see infrared radiation? No, but I can feel it. I can feel it. And so I excited the electrons enough so that they start emitting. The electrons get excited like this,
And they don't stay excited forever. What happens? Eventually they'll settle down. When they settle down, is energy destroyed? No. And so once they're excited to infrared energies, they settle down and emit infrared light. You know that? Will emit infrared light. But you know what? I'm going to heat this more. And do you see that glow? What is that? That's red light. It's starting to emit red light. Red light is visible. And then if I keep heating this, I'm going to, look at it, it's orange now. Red, orange.
Yellow.
And then as I add more and more, as I get the electrons more and more excited and get this hotter and hotter, eventually it'll become white hot piece of metal. I'm not going to heat it to white hot because it'll probably melt. But it'll become white hot. When it's white hot, you know what colors it's emitting? White light is all the colors of the rainbow. And then if I keep heating this, I'm going to eventually start emitting, what's the next? UV and then X-rays and then gamma rays. So I want to stop there. I want to stop at the white light, right? I don't want much UV light emitted.
Is it possible to be like gamma ray from that metal?
No. All right, so you know what this is called a black body. A black body emitter. This is called a black body emitter. What a black body is you know what black bodies do? Do you know why it's black? Why an object's black? Black bodies turn out to absorb all colors of the rainbow. Black objects absorb all colors, therefore they appear black. And so black body emitter is something that absorbs all colors, can also emit all colors. And so when you excite a black body, it should emit all colors of the rainbow. In other words, it should emit white light. And so in other words, what we have is this. The electron energies in this metal are quantized or continuous. The electron energies in this metal are quantized or continuous? Quantized, why? Why is it quantized? What colors are forbidden? What colors were forbidden? What was forbidden? Tell me what types of energies were forbidden.
Anything between red and orange.
Anything between red and orange was forbidden? No, red just blends into orange, you know. There's nothing between because it just blends from one shade of red to orange. That's all. What was forbidden? Nothing. Black body, there's no energies that are forbidden. All energies are allowed. And that makes sense. If you have an electron in a metal, metals have loosely held electrons, right? And so you should be able to excite the electrons in the metal to any energy, right? Let's say a metal here is cruising along at 5 miles an hour. Can it go 6 or does it have to jump to 10? You know, that's a bad analogy because electrons aren't going to be moving at 5 miles an hour. Electrons are moving quite fast. But in other words, if I were to excite an electron here in the metal, can it go any speed it wants? Well, it's pretty. Let me backtrack. If I have an electron in a vacuum, let's say I have an electron in this room, can the electron move at any speed it wants? Let's say I shoot. Remember we were talking about electron guns a long time ago? Mass spectrometer? If I shoot an electron through the room, can the electron get any speed, or are there forbidden speeds for the electron? What are the forbidden speeds of an electron? Well, yeah, that's forbidden, but I'm saying anything below that, what's forbidden? What's forbidden? So if I have an electron out in space, like, you know, the sun,
That's good for business.
do you guys know what the fourth state of matter is? A plasma. And do you know in the sun, there are a whole bunch of free electrons? And those free electrons in the sun, because it's so hot, you know, and the hydrogen gets ionized, what happens when the hydrogen gets ionized? It loses electrons, and the electrons are moving about. Those electrons in the sun, can they have any energy they want within those limits, or are there forbidden energies in the sun? You know, let's just talk about visible. The sun emits white light, right? Are there any colors in the rainbow that are missing, or is it completely continuous? When you went out with a spectroscope, did you see any black areas? This color is missing? Well, if you look closely, there are some colors missing, but they know why. They know why they're missing, because it's not because they're missing, it's because something absorbed them, right? But the sun emits all the colors of the rainbow because there are no forbidden colors. All colors are allowed. This is continuous. The sun is a black body emitter. It emits all colors of the rainbow. Nothing's forbidden, right? The metal, this piece of metal should be a black body emitter. And so what did somebody do? Somebody said, well, look, do you see the metal's getting brown with oxidation? And so how can you protect the metal from getting brown with oxidation like this? Eventually, that oxidation is going to make it brittle, and it's going to crack, right? And it becomes brittle, turns into ceramic. It doesn't conduct electricity very well. And so how can you protect this? You know how you protect this? You protect this in what we call an inert atmosphere. And so you get a piece of glass, you fill the glass up with an inert gas, and then you heat it like this in an inert atmosphere. Do you know what they call that? They call that the light bulb, right? The light bulb is supposed to be a black body emitter. There's a piece of metal in here, tungsten. Tungsten's easy to oxidize at high temperature. To prevent oxidation, you got to make sure there's no oxygen in here. And so you got to fill the bulb up with. Try this. If you want to try this as an experiment, break the light bulb, brand new light bulb, put it in. Well, don't try this as an experiment. You'll shock yourself. And then watch your metal turn into an oxide before your eyes. It'll turn black and then break so easily, right? It doesn't conduct electricity.
Like TVs too, or something like that?
And TV tubes is slightly different, but similar in certain ways. TV tubes are going to be sealed in a vacuum, or not vacuum, but low pressures. Well, anyway, this is a black body emitter. It should emit all colors, right, of light. And so this means that anything with electrons should be a black body. For example, hydrogen. Hydrogen has how many electrons? Let's say an atom of hydrogen, because there are two ways to excite the hydrogen. One, we could heat it up with a flame, or two, we could heat it up with electricity. If we heat up the hydrogen with electricity, we break the HH bond, so we have a hydrogen atom. In a hydrogen atom, what is a hydrogen atom made up of? One proton and one electron. Now the electron in a hydrogen atom, can it go any speed it wants, or are there forbidden speeds? Well, physicists thought it should go any speed it wants. If it goes a little faster, fine. A little faster, no problem. A little slower, no problem. And so any speed that electron wants to go should be allowed. Therefore, the electron in a hydrogen atom should also be a black body. And therefore, a hydrogen lamp should give us white light. Because excite the electron a little bit, excite it a lot, you could excite it anywhere in between. And so we should get black body radiation from this. In other words, we should see white light. Did you see white light coming off there? No, that's helium, but the hydrogen was somewhere around there. Did you see white light coming off there? No, you only saw distinct colors, right? And you saw lots of black. Well, the black, it had it wasn't really black. It would be black if there was nothing on there. The distinct colors were the peaks, and between the peaks are what we call forbidden energies. The peaks are allowed energies. And so in other words, if we have an electron in a hydrogen atom, it can't go any speed at once. And so this would be analogous to you're driving down the road, you can't go any speed you want. It's either 10 miles or 25 miles an hour, but nothing in between. The same thing with electron and hydrogen. It could go this speed, 1, this speed, 2, and you might have not seen these ones because they're smaller. This speed 3, this speed 4. There are only 4 allowed energies for the electron in a hydrogen atom. Everything else is forbidden. And so this is very unusual because the physics of this is very simple. You have a positive charge, a negative charge. If you want more speed, you just have a bigger orbit, right? If you want less speed, less energy, you have a smaller orbit. And so the question is, why doesn't hydrogen act as a black body? And it's not just hydrogen, it's helium, neon, all these you saw, sodium, all these don't. And then the other question is, why does the spatula, the tungsten, act as a black body? Why are these things acting like a black body, but those aren't?
These are here.
Yeah. And so this is the start of the quantum theory. You know, you start off with these observations, and then you start thinking. You start looking for patterns. And so we'll talk about the pattern, but we'll go on a break now.
So tungsten would be white because it's tungsten. So like for these ones, like since you're using different elements like helium and hydrogen, they emit different light.
No, iron is white light, tungsten is white light, a bunch of things give off white light.
Okay, so that's why the other ones are like red light and blue light, like helium and all.
No, tungsten gives off white light in a metal filament, but vaporized tungsten atoms do not give off white light. Vaporized tungsten atoms have forbidden and allowed. We'll talk about it briefly next.
When you say white light, is